Now, the last thing we need to do in this portion of the lecture is to define our loads. Before consulting the code for load combinations, we'll define our service loads. Those are the unfactored loads that are used in the ASD method and that come from our beam formulas directly. Remember the cable analysis section? We recommended that you split your loads into dead and live load for this purpose. So we have three types of loads on the beam: a dead load, a live load, and an earth pressure. Dead load is going to be our cable force purely from the walkway self-weight minus the frictional resistance from the overburden rotated into the same plane as the cable force using the average cable angle. So that's our PT hand back plus our PT walk back dead load version minus our friction times our overburden force times the cosine of our average cable angle. Our live load is just going to be our handrail cable tension and our walkway cable tension, just the live load portion. And our earth pressure is simply that P active value times a cosine of our average cable angle to translate it into the same direction as the front face of the anchor. And this is all drawn here on our free body diagram. Now, because reinforced concrete is designed using the LRFD method, we'll turn to Chapter 5 on loads to find our appropriate load combinations. Now, generally, strength requirements should satisfy U is less than or equal to phi times our nominal strength. So our load combination value less than or equal to our strength reduction factor times the nominal strength of the section, where U is going to be our governing load combination, in which our loads are multiplied by their load factors. These are different than a strength reduction factor, which is multiplied by the nominal strength of the section. By inspection, we see that our governing load combinations will be 1.2 dead load plus 1.6 live load for the full loading case and 1.4 dead load for the hoisting and decking cases. For the full load case, we will include a 1.6 times H term per section 5.3.8, in that H is our earth pressure. Section 5.3.8 specifies that we need to include a 1.6, the value of the earth pressure in the case that the earth pressure is negatively impacting the strength of the section, or working towards the failure of the beam section. Strength reduction factors for our nominal sectional strengths will depend on the failure mode. This is done as a way to control failure. So for example, we design our beams so that the ductile steel will fail first in tension instead of the brittle concrete failing suddenly in compression. And we can read these strength reduction factors from table 21.2.1 of ACI 318. Flexure phi is going to be 0.9. Because that's ductile, we can add a little more capacity. Compression, because it's going to be brittle, is 0.65. Shear and torsion will take a reduction factor of 0.75. And for bearing on concrete, we'll take a reduction factor of 0.6. Now, in the following sections, we will discuss how to calculate the nominal sectional strength for each possible failure mode. And notice that we are going to ignore serviceability design here. Unlike in the towers, because the anchors are buried into the ramp, if cracking occurs and the anchor beam begins to slightly deflect, it will be supported by the ramp fill and the overburden. So as long as the strength requirements are met, we will consider this to be sufficient.